Welcome to lecture 4. So, if you can recall, we were studying motion of a body. We also brought in time. And so we said that the map is now the following. Y is equal to this configuration map, which is of course a vector function, in position of all the particles P and time T. Okay, so time is here, right? And that's why the range or the space occupied by the body is also a function of time. So RT is this configuration map applied to the entire body. Okay, and remember that body is just a collection of particles, abstract collection of particles. Okay, and then we introduced how to write down velocity and acceleration, and we said that the velocity v is some v star of which is a position of particle p and time t. Okay, and likewise the acceleration a is some a star which is a position of the particle p and time t. Okay, and you also saw this acceleration, for example, is simply the second derivative of the configuration map with respect to time, right? It's the partial derivative, keeping the particle fixed, because we always talk of velocity or acceleration of a particle. Okay, and then we, through the map, we could also introduce Lagrangian and Eulerian forms of velocity. So this is the Eulerian form with a bar, which is now a function of the current position y and time t. Okay, and you could recall that this was equated to v star using the inverse map, isn't it? Of sorry, this is okay, v star. Then you have to have the direct map chi of p comma t, and you see that t is present twice here. Okay, and you could also write this, you can also think of the Lagrangian form of velocity, in which case the velocity, it's v hat, and it's a function of the reference configuration, the location of the particle in the reference configuration. And that can again be obtained through this v star, but using this reference map. Okay, and in the last class I mistakenly wrote that the reference map is also a function of time, but reference map is not a function of time. So there is single time present here. All right. Okay, so everyone is good here. Okay, having introduced velocity, and likewise you can also think of acceleration, the Eulerian and Lagrangian forms of acceleration. So let us now talk about, just like we talked of Eulerian and Lagrangian derivatives, spatial derivatives, let us also talk of Eulerian and Lagrangian time derivatives. Okay. So again, it's I think you can very easily guess what would that be. So the Eulerian derivative, for example, has to be applied to the Eulerian function, right? So again, think of let us say temperature theta, isn't it? So there are two forms, theta being a function of either y comma t, which we wrote as theta bar, and in the Lagrangian form, it is theta hat being a function of x comma t. Okay. So what do you mean by Eulerian time derivative? That actually means you have to take the time derivative of the Eulerian theta bar. Okay. So that's del theta bar by del t. So this is done keeping the spatial location y fixed. Okay. So this is at fixed y. So the physical meaning is time derivative keeping the spatial location fixed. All right. Likewise, from here, you can think of del theta hat over del t. So this is at fixed x. So this is keeping the referential position of the particle fixed. Okay. So that's a physical meaning. All right. And then, we also have short notations, just like in case of spatial derivative. You remember you had grad with a small g and big G. So here also, instead of writing this whole thing, we simply write theta bar. Now this is, it's up to you what you want to use. You can either write the full thing just to be clear, or you just use the shorthand notation, theta bar, or theta prime, sorry, this is theta prime. Similarly, for this one, in the book, they use theta with a dot. Okay? And this is also called material time derivative, because you can see that when you're keeping the reference position of the particle fixed, or when the reference position is fixed, this automatically implies that you are also fixing the particle, because at a given reference position, you have a unique particle. But at a given spatial position y, you don't have unique particle, because at different times you have different particle at the same spatial position. But at a given reference position x, you always have a unique particle. So keeping reference position fixed is same as keeping particle fixed. Okay, that's why it's also called material time derivative. Okay, let's see if I have some question. Okay, no question till now. As I have told you, you have liberty to ask me question. So with these notations for Eulerian and Lagrangian time derivatives, can we think of what would again the velocity be? Sorry, this velocity v, if we have this map xi, which is the function of particle p and time t, then of course here, whenever we ask for the velocity of a particle, so we have to track the particle and see how it is changing its position. So here it is clear, and which we also wrote above, that this is simply del x by del t. keeping the particle fixed, isn't it? And of course, you got the two velocities, the Lagrangian v hat and Eulerian v bar. But now supposing that you have v hat and v bar, how do you get accelerations? For example, acceleration a bar, and acceleration a hat. How can we obtain that? Okay, Niladri is asking referential position fixed means by any example. So, see, you have to always think of this picture, a general picture. So this is reference, this is deformed, and then this is your body. So here's the particle P, which has a unique location X in the reference configuration. But its location in the deformed configuration is changing with time. So due to this ref, this map, no, for every X in the reference configuration, you have a unique particle P in the body. Okay. And if you want to have an actual physical example, see, it can be applied to anything. You are just saying, just think of, for example, the flow of water. Water is flowing here. So if you think of a particle, if you want to track a particle, let's say here, this would be moving in time, isn't it? So it does not have a fixed spatial location. The water particle does not have a fixed spatial location. It is changing with time. So therefore, its current position y is a function of time, right? You would say y for this particle P is a function of time. But when you ask what is its reference position, that is not a function of time. So reference position is here, right? It's here. That is not a function of time. It is set by you and it is fixed. Anyway, so proceeding further, the tricky thing comes when we want to relate this A, which I say, so since it is Eulerian, it has to be a function of current position, no, or the spatial position y and t. Okay, and in the Lagrangian form, it has to be a function of the position in the reference configuration. And remember that to each reference configuration, to each reference position, there is a unique particle. Always remember that. With this map, or it can be also clear from this picture. Okay, now what do you think? How can is there some relation between the two? Are these two related to each other? So they are supposed to denote acceleration. So when I say acceleration at a spatial position y and at time t, what does this mean? So literally, as it is written here, it has to mean acceleration at spatial location y and at time t. But you see, velocity and acceleration, they are not of spatial locations. It can't be of spatial location. It has to be of some material. It has to be of some particle. So when I say acceleration at the location y, what would that mean? It would simply mean acceleration of the particle which is at that location y at that time t. Okay, so it just means, so it is equivalent to saying that it is equivalent to acceleration of the particle which is currently at y at time t. Okay. Similarly, what is the meaning of this Lagrangian form? Acceleration as a function of x comma t, where x is the referential position. So does it mean acceleration of the particle in the reference configuration? Does it mean so? Is it implying the acceleration of the particle in the reference configuration? Anybody? Can you make a comment? Well, there are two no's. Anybody? Yes. So all of you are right. It is no. So what does it mean then? It means acceleration of the particle. See, acceleration velocity always has to be in the current position, not in the reference configuration. So acceleration of the particle in the current position, but then of what? Acceleration in the current position, but of what? Of which particle? So this is of course not correct, but then what is correct then? It is acceleration in the current position, or you can say acceleration at time t of the particle which is at x in the reference configuration. You see, so you have to be careful with the words. The particle which is at x in the reference configuration, it is the acceleration of that particle. Okay. So with these physical meaning to the two acceleration functions, it is quite clear that a, for example, in place of y, you could also write the, you remember you had that deformation map function relating reference to directly to current y hat. So that's your deformation map function, isn't it? Y hat of x comma t, and then another t. So this a is this itself, because y, when I say acceleration at the spatial location y, this first argument is then able to tell you of which particle. So you can then relate it to a hat okay, of x comma t. So this is how you can relate the two functions. Now let us see how can we relate the two velocities. How do we relate the two velocities? So this v bar and v hat, how can we relate those two? So can we say that, so v bar of course is a function of y comma t, and v hat is a function of x comma t. So can we say that del by del t on the two sides will be the same? Would you agree with this? Del by del t on the two sides are same. So that's right, it is not correct. You just have to think, once you wrote this, what does it physically mean? So what is the meaning of the left hand side? This means change in velocity with respect to time at the spatial location y, because when you do that derivative you have to keep y fixed. So I'll just write here, this means change in velocity with respect to time at the fixed location y. Right? And what is this right hand side? This is change in velocity with respect to time, keeping reference position x fixed. So when it says keeping reference position x fixed, then you can always invoke this map here and relate the x to the particle. So it is equivalent to saying that change in velocity with respect to time, keeping the particle fixed. So that means you are looking at the change in velocity of a single particle, which from physics you know is acceleration. So this is same as this thing over here. So they are same. But the left hand side, you see left hand side, it says keeping fixed location y. So you are measuring the velocity at the same location y at different times. But you see that at a given location y, you have different particles passing through it at different time. So let us say at t equal to t1, you will measure velocity of particle y1, whereas at t equal to t2, you will measure particle of velocity y2. And then you take their difference and divide by delta t to get this time derivative. But that's not the acceleration, right? Because acceleration is always of a given particle. You have to take the rate of change of velocity of a given particle. But here you are taking the difference of two different particles, right? So this can also be written as velocity, let us say at y comma t plus delta t, or I should say simply t2, let us say at time t2, minus velocity at a location y and say at time t1 divided by t2 minus t1, right? using calculus, and you have to take the limit t2 minus t1 going to 0. Right? That is what the meaning of that partial derivative is. You have to keep y fixed. But when you do that, it is equivalent to saying that it is limit, again the same thing, t2 minus t1 tending to 0. Then it is velocity. You see, keeping y fixed and at different time t2, then you have a different particle. So it's like you have v star of some particle p2 at time t2 minus v star of particle p1 at time t1, and then you are taking the difference t2 minus t1. So this obviously can't be acceleration. In order to have acceleration, this p2 and p1, it must be same, but it is not the same here, therefore it can't be acceleration. Okay, so that's the reason why those two derivatives are not matching. Okay, but then how can we relate those two? Is there any way to relate those two? Then yes, there is a way to relate. So you see, on the left hand side you have Eulerian time derivative, whereas on the right hand side you have Lagrangian time derivative. Okay, and you can see that these two are not the same. Just like Lagrangian and Eulerian spatial derivatives were not the same. The same applies to time derivatives. Okay. So, we can ask this general question, how del theta bar by del t is related to del theta hat by del t. Okay. So let's try to explore that. So let me write down this del theta hat by del t more explicitly. So del theta hat by del t, and I'm saying you have to keep the reference position x fixed. So when you keep the reference position x fixed, it means you write x with respect to some coordinate system e1, e2, e3. You get three components, x1, x2, x3. So you have to keep all the three components fixed. When you say x fixed, that means all the three components are fixed. Okay. So it is same as x1, x2, x3, comma t. Okay. And I'll just write it in index form as follows: del theta by del t, xi, comma t. So writing just xi means I'm meaning all three of them, x1, x2, x3. So similarly, del theta bar by del t is simply del theta bar by del t, and it's function of y, no? So it's y1, y2, y3. Now let me invoke that map and see if we can relate the two. You see, this theta hat of x comma t is same as theta bar of y of x comma t, isn't it? And then another t. Right? We can relate the two functions in this way. And then let us take the time derivative on both the sides. Because this function, you can relate this for every time. This will hold for every time. So now we can take the time derivative. So when we do del by del t here, then you have to do the same thing on the right hand side. Okay, now, and you remember this is done keeping x fixed, so this means x1, x2, x3 is fixed, and this is, by the way, y hat. This is a function y hat, no, it's the function y hat. So this is equivalent to del by del t theta bar. See, we are going very slow. Please don't worry. What is hat, bar? We are going very slow. Just follow me. And you write this from this vector y hat in terms of the three components. So let us say y1 hat, which is a function of x comma t, then y2 hat, that's also a function of x comma t, then y3 hat is also a function of x comma t, right? And finally you have another t. See, right now we are just doing some mathematics, but this will allow us to relate the two derivatives. And then we have to do this del by del t. You see, so we have to, wherever we have time present, you have to take the derivative of all of them. So we have to now apply chain rule. Okay, and see that on the left hand side, the time derivative is such that you have to keep x fixed. So that's the also called material time derivative, right? When you keep x fixed or particle fixed and then take the time derivative, that's like taking material time derivative. So now coming on the right hand side, you can see that all the four arguments are functions of time, right? All the four arguments are functions of time. And understand that when you take the derivative, you don't have to keep y fixed. So this, on the right hand side again, you have to keep x fixed, not y. Then only the two time derivatives will be same, right? Earlier they were not same because one was keeping x fixed and the other was keeping y fixed. But here, if we want to equate the time derivatives, we have to say for both of them keeping x fixed. All right. So coming back here, this is again keeping x fixed. So you come to the first argument, y1 hat. Okay. So we have to apply chain rule, no? This is del theta bar over del y1 into del y1 hat by del t. Okay. And this has to be done keeping x fixed. Again, the second one, del theta bar by del y2 into del y2 hat by del t, keeping x fixed, right? You have to do it for all the arguments, plus del theta bar by del y3 into del y3 hat by del t, keeping x fixed. And then the last one, which is del theta bar by del t, right? The explicit dependence on time, we have to take that derivative also. And this is done keeping all the other arguments fixed. So this is equivalent to saying keeping y fixed. Okay, now come back here again. This is del theta bar by del y1 into, what is this thing? Del y1 hat by del t. What is this? Keeping x fixed is like keeping particle fixed. Anyone, can you say what is this del y1 hat by del t? v hat, but which one? X component of velocity, very good. Or v1, that's right. So this is simply into v1 hat of x comma t, right? Plus del theta bar by del y2 into v2 hat of x comma t. So you have to revise what I taught in the previous class. Okay, always do that before coming to the class, always revise. Plus del theta bar by del y3 into v3 hat of x comma t. And then the last one, del theta bar by del t, keeping y fixed. Okay. Now, what can we say about the first three terms? Can we write this as follows: del theta bar by del y1, del theta bar by del y2, del theta bar by del y3, multiplied with v1 hat, v2 hat, and v3 hat. Can we do that? You see, it's a 1 by 3 matrix multiplied with 3 by 1 matrix. It will give you 1 by 1. And the last term is simply del theta bar by del t, keeping y fixed. Somebody is asking, why is the last one keeping y fixed? Because you see, when you're coming from here to here, the first one, when you do the first one, you do it keeping all other arguments fixed, right? That's how you do chain rule. If a function is of several variables and you want to take the derivative, you first take the derivative, first one keeping others fixed, second one keeping others fixed, third one keeping others fixed, fourth one keeping others fixed. When you do the fourth one this time, keeping other fixed, so others are the three components of y. So when you fix all the three components of y, that is like fixing y. Okay? So that's the meaning here. Now, again, what is this thing over here? The first thing, isn't this the gradient of theta bar? But which gradient? Is this the Lagrangian gradient or the Eulerian gradient? Anyone? Okay, somebody is saying, several people are saying Lagrangian gradient. Some are saying Eulerian. See, it is Eulerian gradient because the derivative is with respect to y, right? And y is the current position. It's the spatial location. That's why it's Eulerian gradient. Lagrangian gradient is when you take the derivative with respect to referential positions, referential coordinates. Okay? So, therefore, you could either write it as, let me write this small g grad theta bar. Okay? And this is then multiplied, or you see, it's also dot product, no? A vector dotted with the velocity vector, v hat, isn't it? Plus this del theta bar by del t at fixed y. Okay? So you see, that's how we have related the two. So on the left hand side, we had del theta hat by del t at fixed x. So when you relate, this is what you get. So you can see that you have an extra term here. And this v hat, you can also replace this with v bar, right? So this is, I'll just write here, grad theta bar of y comma t dot with v bar of y comma t plus del theta bar by del t of y comma t. So you see the right hand side is now completely Eulerian. All the terms are Eulerian. You just have to remember to replace y with y hat of x comma t on the right hand side, and then you can equate the two. So this has to be substitute, and then they become equal. Okay, you see we have a very nice formula, no? So going in the same direction, you can also relate the Lagrangian and Eulerian gradients of, Lagrangian and Eulerian derivatives of velocity. And when you do that, what you get is del v hat by del t, keeping x fixed, that is equal to, you see, whatever you are taking the derivative, no, you have to take the gradient of that. So take the gradient of velocity, Eulerian gradient, and then this gets multiplied with velocity itself. Plus del v by del t. Okay, and remember that this thing is the gradient of a vector. Here it was a gradient of a scalar quantity, so it gave you a vector. But the gradient of a vector gives you a second order tensor. So I think you have already learned this in math class, right? So this is now a second order tensor, which when you express in a coordinate system, you'll get a matrix. So gradient increases the order of a tensor. So I hope everybody knows about this. Okay, and now you can see you are able to relate Lagrangian time derivative of velocity with Eulerian time derivative of velocity. And you can see that those two are not the same. That was the original question. Those two are not the same. So as we saw earlier, the Lagrangian time derivative is also called material time derivative, right? And this is what is giving you acceleration. So that's acceleration. This is also material. So what we did here was material time derivative. So what we see from here, that acceleration has got two terms. The second one is what is called local part of acceleration. They also say local acceleration, because why local? It is keeping y fixed, no? So when you are in the space, you fix the spatial location y and then measuring the rate of change of velocity. So that's why we say it's the local part of acceleration. And this part, that's called the convective part of acceleration. So that is arising because of the convection of particles. Convective part of acceleration. So in fluid mechanics, you must have come across this, that acceleration has two parts. Any questions so far? So I'm going to stop here, and this is the end of chapter 1 from the book. Please revise chapter. The book has got many more things. Everything is important. And also revise my video lecture. And I'll now unmute you. You can ask me questions. Yeah.
Hello, sir.
Yes, tell me.
Sir, in the last step, the velocity was till Lagrangian,
You mean
and then
here?
yes, sir, the first line.
Yeah, right. It is Lagrangian here.
Like, how did that transition like went to Eulerian in one step? Yeah, that
So
only, sir.
see, when you are doing that, you just have to be careful that, see, this Lagrangian means this is v hat of x comma t,
Yes, sir.
So you can always equate this to v bar of y hat of x comma t, right? That's how you relate the two velocities.
Yes, sir. Got it. Got it.
Yeah, and so that is what I have done here. So when I write y here, it is y hat of x comma t. You see this thing also I wrote here, no? Wherever you have y, you have to replace that with this function.
Yeah, thank you, sir.
Okay. When you say y hat, no, y hat is a function, okay? And it's a function of x and t. So with y hat, it is clear that you are looking at a particle which is at x in the reference position. So you can then uniquely point to a particle. When you just say y without the hat, if you just say y, so y is just a position in the three-dimensional space, okay? Without the hat, it is just a position in the three-dimensional space. And at that position, you can have different particles passing through at different times. But when you say y hat, this function, it is supposed to imply this deformation map. Okay, and when you fix x, if you fix x, then y does not get fixed. So from here, when you try to get the output, let us say you say y equal to y hat, when you fix x, then y does not get fixed. But here, when you are saying just y, and you are saying then that, okay, let us fix y. So here, when you say fix y, you are not referring to this y hat. You are just saying fix a position in the 3D space. Just think of it from physics. When you fix y is just a variable, it is not a function. When you fix y, it is like fixing a position in 3D space. And then you know that at different time, different particles will come to it.
So when we take the inverse of xi, so we consider this uh, y tilde only, not y hat, right? I mean, when we are finding the particle p by tracing its location, current location. So in that case, we are using this y tilde means the current location, which is not varying with time.
See,
I
your
mean,
question
you
is not so first, okay. So your question is not really clear, but you are talking about some inverse map, okay? Isn't that? So
sir, please write P is equal to xi inverse y tilde comma t.
P equal to chi inverse
Y tilde
y
comma t.
tilde comma t.
Yes. So what is this y in this case? This y hat or only y?
This is just y. This is not hat. This is simply y tilde. Don't call it y tilde, just say y. Okay.
Okay, okay.
Yeah.
So it is not a function of x tilde.
Yeah, right now it is just a y. It is not a function of x tilde, but you can always do that also. But with in this function, it is just a spatial location y.
Okay, so that's what I wanted to ask.
Okay, it is just a spatial location y. Okay, very good question. Any other question? So thank you everyone.